Hello. In this video we're going to be talking about a mathematical technique that we're going to be using a lot in thermodynamics, and this is the idea of partial derivatives. And this comes from the fact that we're going to be dealing with functions that are functions of multiple variables. So when you learned calculus, probably starting in high school or your first year at college, you learned about, say, functions. Y is a function of, or f is a function of x, right? So there's one variable. Maybe this is like 2x plus 3. Or whatever like that. So we just have one variable to worry about. But in thermodynamics, we're often looking at things like the ideal gas law. Say if we write the ideal gas law just looking at pressure, P equals nRT over V. Now we can consider all three of these to be variables, and so we could say pressure is a function of N, T, and V. And now it's not so clear. We can't just use the same rules that we've used previously if we want to take the derivative of this function to find out what is the derivative. So how do we do that? And that's where this idea of partial derivatives comes in. And here we're going to look at derivatives of one variable at a time. And so, for example, say we want to take the derivative of the ideal gas law with respect to the number of moles. So we write that as dp dn. And you notice these d's are like italicized. These are not, normally we write a derivative like this, right? dp dn or something like this. This would not be a partial derivative, though. So that's this notation here with this sort of cursive italicized d. And then we put parentheses around it, and then as subscripts, we list the variables that are being held constant. So in this case, we're holding temperature and volume constant, but we are taking the derivative with respect to the number of moles n. And to do this derivative, we would just treat t and v as if they were constants in the equation. So if we look back at our original equation here, we take the derivative of n. We can treat r, t, and v as all being constants. Then this would just be like a constant times x, and so we just get the constants that are left over. So the derivative here would just be rt over v. So doing partial derivatives is not, it's the same rules you've learned for all the other derivatives, and so this is fairly straightforward. So we can do this as well for, the other variables. Let's say we want to look at dp dt, holding n and v constant. That one's going to be pretty straightforward. That's nr over v, because n and v are constant. And then we can also look at dp dv at constant n and t. And now we have a 1 over v situation. So we'll get minus nRT over v squared. Right, so we can treat this as v to the minus 1. Okay, and then if we want to do second derivatives, same thing in terms of just writing notation. Let's say we want to do second derivative of p with respect to n. We write it this way. And in this case, that would give us 0 because there's now no n left behind. Right, so we could do this for the other ones as well. So one follow-up to the idea of second derivatives is what we call cross derivatives, and these will show up later in the class. So we'll go ahead and cover them now, just for completeness here. Let's go ahead and rewrite the ideal gas law with just two variables. All right, so this is cross derivatives, and we can do this by combining the n and v into a molar volume. So let's say we have p equals rt over v bar. Now we just have p as a function of t and v bar. And we can take two partial derivatives, right? So we can do dp dt at constant v bar, and that'll give us, all right, so if v bar is constant, we're just going to get r over v bar. And we can do the other partial derivative, dp dv bar, at constant t, and that'll give us minus rt over v bar squared. Now we have two derivatives here, sort of two different variables we can look at, and the cross derivative is now we take these derivatives and take the derivative with respect to the other variable. So we could say take this whole thing, so our dp dt at constant v bar, take the derivative of this with respect to now v bar, keeping t constant. All right, so we can just go ahead and now substitute d derivative with respect to v bar, and then what was the value of this derivative? We take this here and substitute it here. So we put r over v bar, constant t, and we'll get minus r over v bar squared. Now, if we take the other derivative we have here that we did with respect to v bar, we can do the same thing, and now take the derivative, partial derivative with respect to temperature, dp dv bar at constant t, all of that constant v bar. We can do the same derivative, the opposite cross derivative, right? So again, we'll make a substitution. This is going to go into for this. So we get derivative with respect to temperature of minus RT over V bar squared at constant V bar. And that's going to be straightforward. That's just minus R over V bar squared. Now, what you probably haven't noticed is that these two are equal to each other. And that's not a coincidence. So this isn't just like the special case that I picked. In general, cross derivatives are equal to each other. We're not going to like prove this, but it is something you can prove. And we're going to rely on this fact in later in the class to get some useful relationships between different thermodynamic variables. So we'll go ahead and pause there. Oh, one last thing just on notation. Often cross derivatives are written a little bit easier. So something like this instead, where you don't have to put all of the things that you're holding constant. So cross derivative of p, you would take the derivative with respect to t first and then v bar, but it doesn't matter the order. So we could say this is equal to this. Right, so the order on the bottom just tells you which order you would do the derivatives in. So we'll pause there, and there's one more topic related to partial derivatives that we will cover in the next video.